Hey everybody, welcome to our Microsoft Build session. I'm here today with Diego, Milos, Alin, and Irem.
Hi everyone.
Hello everyone, hi.
Hello. And they're going to be talking to us today about running PyTorch on Windows on ARM and using GitHub Runners for that. So Diego, why don't you go ahead and start us off?
Cool. Hello everyone, my name is Diego Russo and I work as a principal software engineer at ARM. Thanks for joining this session. Over the next 20 minutes, we'll take a look at how the new Windows ARM64 GitHub Runners have opened the door for key open source projects like CPython and PyTorch to build, validate, and deploy natively for Windows on ARM. This progress has been made possible through a strong collaboration between ARM, Microsoft, and Meta. We'll start with an overview of the GitHub Runners and how you can use them to build and test on Windows on ARM. Then we'll look at PyTorch and what was updated to make it run well on Windows on ARM. And finally, we'll wrap things up with a quick demo and a call to action. Let's start with the Windows ARM64 hosted runners available on GitHub. These runners are free to use in the public repositories, which is a big win for open source communities. It means that developers can now build, test, validate, and even deploy the software natively on ARM platforms without needing special hardware or extra setup. In the past, supporting Windows on ARM often meant setting up cross-compilation toolchains or running your CI jobs in a virtualized environment. That added a lot of overhead and complexity. With these runners, that's no longer necessary. You get the same GitHub Actions experience you're used to, just with a native ARM performance. And because the runners are hosted, setup is minimal, and you can focus entirely on your workflows. These also translate into faster, more streamlined CI pipelines, especially for projects that are already targeting ARM platforms. And we are already seeing major open source projects taking advantage of these. CPython, PyTorch, and even LLVM are now using these runners to support Windows on ARM builds more easily. Let's take a closer look at what's inside the Windows ARM64 runner image. These runners use a Windows 11 desktop image running in headless CI environment, just like the other GitHub hosted runners.
Yep.
While the base system is fully featured, it's specifically tuned for automated workflows. The image comes with pre-installed with a wide range of essential developer tools like compilers, SDKs, scripting languages, and build systems. So you can hit the ground running with a little to no setup. Okay. You can find the full list of installed software in the Partner Runner Images GitHub repository. And I've included a screenshot of it here on the slide for reference. This image was built in partnership with ARM Ltd, so it's tested and optimized to work well on ARM hardware. It also supports a wide range of common use cases right off the box. This includes CMake, Python, Java, .NET, and many more. So you can get started quickly. And because it is optimized for performance and compatibility on ARM hardware, you get a fast, reliable, and production-ready environment from the start. Let's take a look at how CPython, the reference implementation of Python, is using Windows ARM64 runners. CPython was the first major project to adopt these runners. It was also an early test case for running continuous integration natively on Windows on ARM using GitHub Actions. The project now fully compiles, executes, and validates on ARM across all supported operating systems, Linux, macOS, and now Windows. And enabling this is incredibly straightforward. you simply add the Windows 11 ARM label to the runs on field in your workflow configuration file, as you can see in the screenshot on the slide. The rest of the CI logic remains unchanged. This support not only ensures that Python behaves correctly on ARM hardware, it also helps the maintainer catch architecture-specific issues early in development. And because Python is so widely used, it serves as a reference implementation for other open source projects looking to support Windows on ARM. It shows how easy it is to integrate these runners and gain native coverage on ARM platforms. Now, I'll pass it to Milos Puzovic from ARM, who will explain how PyTorch was modified to run natively on Windows on ARM.
Thanks, Diego. So one of the applications that we enable to be able to run on Windows is PyTorch. As you can see here, the PyTorch software stack is very complex. So if you want to be able to run one model, for example, image classification or object detection, you are going to build it using a large number of the operators. And if you want to run those operators efficiently on your target architecture, in this case ARM, there is a fairly deep software stack that is required in order to be able to execute it efficiently. So for example, you might start with an operator such as a linear layer that is going to be mapped to A10 library. And then from this A10 library, as you can see on this image, there are 4 different paths that can be taken in order to be able to efficiently execute and utilize in-core accelerators that are available on ARM. So for example, one path that you can take is actually via ARM Compute Library, 1DNN and IDEEP, while the other path is by leveraging ARM Performance Library, which is a library that has been used in order to enable the fast execution of PyTorch on ARM. Next slide. The reason for having so many different paths is because of the framework tax that is involved when integrating these different libraries with PyTorch software stack. Each library can provide, each library is going to have a different tax that it needs to pay as the cost of integration. So although, for example, if you have 2 different libraries like ARM Compute Library and 1DNN, sometimes 1DNN might actually be faster when executing certain operators, but when integrating it with the PyTorch, there is much higher tax that needs to be paid. So it might be worth integrating ARM Compute Library with PyTorch directly. So that is one of the main reasons why the PyTorch software stack is very deep. And in the next part of the talk, Irem is going to demonstrate how all of this was enabled to run efficiently on ARM.
Thank you, Milos. Hi, everyone. I'm Irem, and today I have exciting news that many of you have been waiting for. PyTorch and, of course, libtorch are now officially available on Windows ARM machines with 2.7 release. This is the result of ongoing collaboration between Microsoft, Meta, and ARM. As part of our internal development, we have used Copilot plus PCs extensively to build and test PyTorch, ensuring the optimal reliability for all Windows ARM users. Additionally, we have incorporated APL, ARM performance libraries, as our last library in PyTorch, just like Milos just explained and provided the details for. So getting started with PyTorch. For those who are ready to start using PyTorch on Windows on ARM, here are a few steps to follow. Firstly, please ensure that your machines have the following prerequisite software installed: Visual Studio, Rust, and Python. And to access the latest features and fixes immediately, nightly builds are currently available. You can easily install it by entering the comments shown on the slide. Alternatively, a stable version of PyTorch is available for direct download through the official website, pytorch.org. Thank you for your attention. We are looking forward to your feedback on Windows ARM version of PyTorch. Now, I would like to hand the things to Alin for his demo. Thank you.
Thank you, Irem. Okay, so I'm extremely excited to be presenting today. Next slide. Okay, I have prepared a small style transfer demo to show all of you what the new PyTorch and NumPy might be capable of. Style transfer models take the artistic style of one image and apply it to the contents of another. Here are some of the results that we achieved. I will now walk you through a video recording of the entire setup process. Everything I need for this presentation is already inside this demo test folder. To get started, let's create a fresh Python virtual environment for the project. This step is important because it allows us to isolate our project dependencies from the global Python setup. Now, let's get back to the exciting bit. We've been working on this for quite some time, and we are extremely happy to share that there's an official PyTorch distribution for Windows on ARM. This is a big step forward in making machine learning more accessible for different platforms. I will be installing the latest nightly version of the package, as it gives us early access to the features and the most up-to-date improvements. Let's wait a bit for the dependencies to get installed. And voila, we now have the newest PyTorch package under Copilot. Another important dependency that we need is torch vision. I have a specially built rule of torch vision that I'm using because it is not yet officially distributed for Windows. We understand how important these tools are, so do not worry. We are actively working on expanding the Torch ecosystem for Windows, and nightly versions for both Torch Audio and Torch Vision packages are on the way. Let's wait for the package and its dependencies to install, and then we can proceed to run the model. Okay, now that we have everything we need, let's run our model. Okay, I will show you what I'm using. And for this demo, I am using a pre-trained VTG19 model that's officially distributed by PyTorch. The model takes 2 pictures, a content image, and a style. Let's check them. The content picture is this cat photo, and the style that we're going to apply on it, it's nice, right? I set the model to run for 100 epochs. Let's speed up the training a little and wait for the results. As you can see, the losses are dropping. So now let's take the let's zoom. And amazing. We now have this nice blended mosaic. This is just one of the many things that AI passionates will now be able to do under Copilot feeds. That's it for the demo. So thanks everyone for the attention. We are looking forward to getting any suggestions, questions, or feedback you might have. And if you want to interact with us directly, you can do so on the PyTorch GitHub backlog. And yeah, I think that's it.
Thanks, Alin, for the demo. It's always great to see things work in practice. To wrap up, I want to leave you with a call to action. More and more open source projects are now running on Windows on ARM, thanks to these free hosted runners. This includes major infrastructures, efforts like CPython, and it is what makes a native PyTorch or Windows on ARM possible and accessible to a broader community. If you are contributing to an open source project, this is a great time to add Windows ARM64 runners to your CI pipeline. It's just one line in your GitHub Actions workflow, and it gives your users a first-class experience on ARM platforms. You can also collaborate with upstream projects to coordinate builds and testing, whether you're working in AI, web frameworks, programming languages, or libraries. If you have suggestions or run into issues, head to the Partner Runner Images repository. That's the central place for feedback, questions, and improvements to the image itself. And if you are in a position to contribute, whether it's a CI configuration, documentation, or validating builds across ARM platforms, your contribution can really accelerate support and stability across the ecosystem. Having these runners accessible is what enables open source projects like PyTorch and CPython to work on Windows on ARM, to grow and to reach even more developers. Thanks for listening to this session, and let's keep building.
All right. Thank you to all of our speakers who joined us today.
Thank you so much.
Thank you.